بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على سيدنا محمد وعلى آله وصحبه أجمعين. Good afternoon, evening, everyone, and thank you for joining this first lecture related to Chapter 1 entitled Grid Computing. So, before starting this lecture, you are expected to be able, through this first part of Lecture 1, to first define the importance of grid computing, define the concept of distributed architectures and its utilities. Third, explain the different characteristics of the distributed systems. Four, explain how to create or the creation of a grid computing on different levels. And finally, explain the different application area of grid computing. This is the outline or the main content of this chapter, in which we will cover the following topics or subtopics. We will talk about grid computing, also talking about distributed architectures, focusing on the main characteristics of the distributed systems. After that, we will learn how to create a grid computing by highlighting also the different types of grid computing. And finally, we will highlight some application area of grid computing. Well, a grid computing, in fact, is a distributed architecture that uses a group of computers to combine resources and work together. Also, grid computing is defined as a distributed architecture of multiple computers connected by networks that work together to accomplish a joint tasks. The system operates on a data grid where computers interact to coordinate jobs at hand. Also, these tasks are compute intensive and difficult for a single machine to handle. Several machines on a network collaborate under a common protocol and work as a single virtual supercomputer to get complex tasks done. So this offers a powerful virtualization by creating a single system image that grants users and applications seamless access to IT capabilities. In fact, a typical grid computing network consists of three main machine types, which are control node, known also as server, provider, known also as grid node, and user. What we mean by control node? A control node is a server or a group of servers that administers the entire network and maintains the record for resources in a network pool. For the second type, which is provider or a grid node, a provider or grid node is a computer that contributes its resources to the network resource pool. Finally, or the last type, which refers to user, a user refers to the computer that uses the resources on the network to complete the tasks. So, grid computing operates by running specialized software on every computer involved in the grid network. The software coordinates and manages all the tasks of the grid. Fundamentally, the software segregates the main task into subtasks and assigns the subtasks to each computer. This allows all the computers to work simultaneously on their respective subtasks. Okay. Upon completion of the subtasks, the outputs of all computers are aggregated to complete the larger main task. The software allows computers to communicate and share information on the portion of the subtask being carried out. As a result, the computers can consolidate and deliver a combined output for the assigned main tasks. Also, grid computing can be viewed as a subset of distributed computing, where a virtual supercomputer integrates the resources of several independent computers that are distributed across geographies. So, computer or computers participating in a grid contribute resources such as processing power, network bandwidth, and storage capacity to perform operations requiring high computational power. The other grid architecture looks like a single computing entity. In grid computing, each computing task is broken into small fragments and distributed across computing nodes for efficient execution. Each fragment is processed in parallel, and as a result, a complex task is accomplished in less time. Okay, let's, for example, consider an equation x equal to 4/7 plus 3 multiple 9 plus 2 multiple 5. In the classical method, when running this equation, and which will be executed on a single machine, these take more time. Contrarily to the distributed computing, where each operation or this equation will be divided into three main operations. So we will execute 4 multiple 7 on a node, 3 multiple 9 on another node, and 2 multiple 5 on also another node. Each node execute this multiplication and provide a resource. Finally, all the obtained results will be combined to get or to have one final output. Okay. So grid computing combines the involved steps related to this equation due to the multiplicity of available resources. So this implies fewer steps and shorter time frames. In fact, grid computing is enabled via an open set of standards and protocols such as Open Grid Services Architecture, known as OGSA, that allow, in fact, communication across heterogeneous systems and environments that are geographically dispersed. So, with grid computing, organizations can pool resources and computing for high-weighted tasks or share them across networks to allow collaboration. Enterprises can thus optimize computing and resources perfectly, irrespective of their location. Okay. Here, it's also important to address the main key components of any grid computing. As explained before, a grid computing environment consists of a set of primary grid components. As grid designs and their expected usage vary, specific components may or may not always be a part of the grid network. These components can be combined to form a hybrid component in specific scenarios. Also, the combination of elements may differ depending on use cases. Understanding their rules can help also while developing grid-enabled applications. Now, let's understand these key components related to a grid computing environment, and which can be summarized in 5 components. First, user interface. Second, security. Third, scheduler or scheduling. 4, data management. And 5, workload and resource management. Let's explain the first component, which is the user interface. As you know, today, users are well versed with web portals. They provide a single interface that allows users to view a wide variety of information. Similarly, a grid portal offers an interface that enables users to launch application with a resource provided by the grid. The interface has a portal style to help users query and execute various functions on the grid effectively. A grid user views a single large virtual computer offering computing resources similar to an internet user who views a unified instance of content on the web. This is the definition of the user interface. Secondly, or the second component, related to security. So, security is one of the major concerns for any grid computing environment. Security mechanisms can include, for example, authentication, authorization, data encryption, and others. So, grid security infrastructure, known as GSI, is an important ingredient here. It outlines specifications that establish secret and tamper-proof communication between software entities operating in a grid network. It includes also OpenSSL implementation and provides a single sign-on mechanism for users to perform actions within the grid. It offers robust security by providing authentication and authorization mechanism for system protection. For the third component, which is scheduler or scheduling, on identifying the resources, the next step is to schedule the task to run on them. A scheduler may not be needed if standalone tasks are to be executed but do not showcase interdependencies. However, if you want to run specific tasks concurrently that require inter-process communication, the job scheduler would surface to coordinate the execution of different subtasks. Moreover, schedulers of different levels operate in a grid environment. For example, a cluster may represent an independent resource with its own scheduler to manage the nodes it contains. Hence, a high-level scheduler may sometimes be required to accomplish the task done on the cluster, while the cluster employs its own separate scheduler to handle work on its individual nodes. The third component, the fourth component, which is the data management. Data management is crucial for any grid environment. So a secure and reliable mechanism to move or make any data or application module accessible to various nodes within the grid is necessary. It offers a data management component called grid access to secondary storage, known as GASS. It includes the grid FTP built on the standard FTP protocol and utilizes GSI for user authentication and authorization. After authentication, the user can move files using the grid FTP facility without going through the login process at every node. Finally, the last component, which refers to workload and resource management. The workload and resource component enables the actual launch of a job on a particular resource. Also checks its status and retrieves the results when the job is completed. Say a user wants to execute an application on the grid. In that case, the application should be aware of the available resources on the grid to take up the workload. So it interacts with the workload manager to determine the resource availability and update the status accordingly. This, in fact, helps in efficient workload and resource management for various nodes on the grid. Nice. The main problematic when using grid computing is the computational or the computation complexity, which is really a major concern. What we mean by computation complexity? This is in the case if we run all the tasks or focusing all the tasks to one single machine. And this is the reason why the distributed computing is appeared. So a computation complexity is a very important topic. It concerns the estimation of how hard or easy a problem can be solved computationally. However, the computational complexity will not answer the actual computation time to be taken to solve a particular problem or problem instance, because the actual implementations will depend on other factors such as hardware and or software. Therefore, the complexity is an estimate of the order or number of computational operations rather than time. Loosely speaking, computational complexity and classes are closely associated with Turing machines. A Turing machine can be considered as an abstract machine which can read an input and manipulate one operation at a time according to predefined rules. In general, a Turing machine is capable of carrying out the computation or the computation of any computable function. Since rules are fixed, one action is carried out at a time. So, such a Turing machine become deterministic, called a deterministic Turing machine. On the other hand, if more than one action is allowed and symbol manipulation can have multiple branches, then the transition on the machine may depend on the current states. Multiple decision structures can lead to non-deterministic characteristics, and we often refer to such a Turing machine as a non-deterministic Turing machine. In the computer science literature, complexity classes are often used for describing different levels of computational complexity. Through the rigorous definition requires other mathematical concepts. We can loosely define the complexity class as a set of decision problems that are computable in terms of a Turing machine, subject to the constraint of a fixed resource. Okay. Also, the grid consists of user computers that provide resources like processing power and storage, grid middleware software to coordinate workloads across the system, and nodes like a central control server that assigns tasks and aggregates results. Together, these components function as a unified virtual supercomputer that offers a greater computational power, storage, and efficiency than any single machine could provide. So by dividing complex jobs into pieces and farming them out to available nodes for parallel processing, grids can complete analysis, simulations, and other data-heavy workloads faster and at a lower cost than conventional alternatives. Let's focus on these main elements, which are nodes, networks, software, protocols. What we mean by nodes? A node, in fact, refers to a computer or server that is part of the grid network, contributing its unused computing resource, such, for example, CPU, memory, and storage. So nodes can perform other related tasks and can often switch between roles depending on the needs of the grid network. For the nodes, there are three main types: control, provider, and user. For the control, which administers the network and manages resource allocation. For the provider, which shares the resources for grid computing. And for the user, which requires resources shared by other computers in the grid computing system. So the nodes can include servers or PCs, all loosely linked together over the internet or other networks and commonly distributed across multiple geographic regions. The second element, which is networks. In grid computing, networks are the backbone that connects multiple computers, often geographically distributed, to work together to accomplish joint tasks. These networks enable the sharing, selection, and aggregation of resources distributed across multiple administrative domains based on their availability, capacity, performance, cost, and user quality of service requirements. Grid computing networks can be homogeneous, consisting of machines with similar platforms using the same operating system, or heterogeneous, with machines running on various operating systems. The third element, which is about software, control software plays a crucial role in managing and coordinating tasks across the grid. The software, often referred to as a grid middleware, which is a specialized application that connects computing resources in grid operation with high-level applications. It runs on every computer involved in the grid network. So the control software's primary function is to break down the main task into subtasks and assign these subtasks to each computer in the grid. This allows, in fact, all the computers to work simultaneously on their respective subtasks, thereby enhancing the efficiency of the computational process. Once the subtasks are completed, the control software aggregates the outputs of all hardware to complete the larger main task. In addition to task management, the control software also handles requests for additional processing power from the grid computing system. It controls the user sharing of available resources to prevent overloading the grid hardware. Moreover, the control software provide security to prevent mistakes or errors. The fourth and the last element, which refers to protocols. Grid computing networks rely on a set of standards and protocols to enable communication across diverse, geographically dispersed systems. These protocols are crucial for implementing services that facilitate coordinated resource sharing across different organizations. So, grid protocols can be classified into several categories based on the activity they handle, and which are, or the first category is the network communication and data transfer protocols. The second category is the information security protocols. The third category, which is the resource information protocols. The fourth category, which refers to management protocols. And the last category, which is the interface protocols. What we mean by network communication and data transfer protocols. This kind of protocols handles the communication and data transfer between different nodes in the grid. They ensure that data is correctly sent and received across the network. This is for the network communication and data transfer protocols. The second category is the information security protocols, and which is responsible for maintaining the security of the grid. They handle tasks such as authentication, authorization, and encryption to protect data and resources from unauthorized access. The third category, which is resource information protocols. These protocols manage the information about the resources available in the grid. So they keep track of the status and help in allocation and scheduling. The fifth category, related to management protocols. In fact, these protocols oversee the other operation of the grid. They handle tasks such job submission, monitoring, and error handling. The last category, which is the interface protocols, it provides a user interface for interacting with the grid. They allow users to submit jobs, monitor their status, and retrieve results. Examples of specific grid protocols include the Open Grid Services Architecture, OGSA, and the sample grid protocol. OGSA provides a framework for data sharing and resource management, while the sample grid protocol is an open source package that includes the protocol and software tools needed to set up a computational grid. Okay. Now let's talk about the distributed systems. And this is the main solution based for any grid computing. A distributed system is a set of independent, autonomous elements known as machines connected by communication system equipped with software dedicated to coordinating the system's activities and sharing its resources. The elements have processing executed or done by processor and storage done by memory or disk functions. These elements, in fact, collaborate with each other as a single coherent system to meet the user's objectives. Here we have example of applying distributed systems. This form of computing is used in various fields to tackle large computational tasks that would be too resource intensive or time consuming for a single computer. Here are some key applications and use cases of grid computing, and which can be summarized in 5 examples. The first example is the scientific research. Grid computing is extensively used in scientific research to evaluate and store large amount of data. It also enables scientists worldwide to collaborate and share computational resources, thereby accelerating research processes and facilitating the handling of complex scientific problems. The second example is about engineering. For engineers, grid computing has significantly reduced the cost of resource-intensive engineering applications. For example, industries such as automotive and aerospace, which require intensive testing facilities and collaborative design efforts, have adopted, in fact, grid computing to speed up time-consuming procedures. The third example is the data analysis. With the explosion of data from various sources like IoT devices, Internet of Things, scientific instruments, and smart gadgets, grid computing plays a crucial role in collecting, storing, and analyzing data. It helps in interpreting the data and observing patterns to synthesize knowledge. The fourth example is for the weather forecasting. meteorologists, meteorologists, sorry, use grid computing to collect and compute massive amounts of data from various locations for weather forecasting. This technology allows for the efficient handling of such large data sets and aids in making accurate weather predictions. The last example is about healthcare. In the healthcare industry, grid computing is used to store and analyze massive amount of patient data, aiding in medical research and development. Now, let's talk about the main characteristics of any distributed systems, and which can be summarized in 4 main characteristics: flexibility, transparency, reliability, and performance. So now that we get what distributed systems are, we can start to assign key features to them. So here is what good distributed systems have in common. Let's start by the scalability. Scalability is the ability to grow as the size of the workload increases is an essential feature of distributed systems, accomplished by adding additional processing units or nodes to the network as needed. For the concurrency, as mentioned, distributed system components run simultaneously. They are also characterized by the lack of a global clock, when tasks occur out of the sequence and at different rates. For the availability and fault tolerance, if one node fails, the remaining nodes can continue to operate without disrupting the overall computation. For the heterogeneity, in most distributed systems, the nodes and components are often asynchronous, with different hardware, middleware, software, and operating systems. This, in fact, allows the distributed systems to be extended with the addition of new components. For the replication, distributed systems enable shared information and messaging, ensuring consistency between redundant resources, such as software or hardware components, improving fault tolerance, reliability, and accessibility. For the transparency, the end user sees a distributed system as a single computational unit rather than as its underlying parts, allowing users to interact with a single logical device rather than being concerned with the system architecture. Here is also it's also important to highlight the benefits and the challenges or risks of any distributed system. Distributed systems offer a number of advantages over monolithic or single systems, and which are scalability and flexibility, fault tolerance, reliability, speed, and distribution. Now we are talking about the advantages of the distributed systems. For the scalability and flexibility, it is easier to add computing power as the need for services grows. In most cases today, you can spin up servers to a distributed system on the fly, increasing performance and further reducing time to completion. For the fault tolerance, distributed systems reduce the risk involved with having a single point of failure, bolstering reliability and fault tolerance. For the reliability, a well-designed distributed system can withstand failures in one or more of its nodes without severely impacting performance. In a monolithic system, the entire application goes down if the server goes down. For the speed, a heavy traffic can bog down single servers when traffic gets heavy, impacting performance for everyone. So the scalability of distributed databases and other distributed systems makes them easier to maintain and also sustain high performance levels. The last advantage, which is about the geo distribution. Distributed content delivery is both intuitive for any internet user and vital for global organizations. Okay. Now, let's talk about some challenges for the distributed systems. The first, or which can be summarized in 5 main challenges: increasing opportunity for failure, synchronization process challenges, imperfect scalability, more complex security, and increasing complexity. So these challenges will be explained, inshallah, in the next record related to the second part of chapter 1. So this is what we have today for this lecture. Thank you very much, and see you, inshallah, in the next lecture. Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh.